Hello guys. Today we are going to discuss a dynamic programming approach. There is something called a dynamic programming template, with which we can almost solve any dynamic programming problem. So we'll discuss the template, then we'll take a Fibonacci number example. We'll solve it using dynamic programming, and we'll apply the template and see how it helps. So basically, before applying the template, we need to identify whether the problem is can be solved using dynamic programming or not. So what dynamic programming basically is, it's just a buzzword, I believe. It's just using caching. So what we can say it as a caching uh, mechanism, right? So we calculate something, we store it in cache, while we again want to calculate that thing again. So first we check in cache that if it exists, and if it's not, then we calculate, and if it exists, run it, we provide the value from cache. That's simple, nothing more um, about the dynamic programming. So it's just a buzzword actually. We can say it's a caching technique. So what is the dynamic programming problem characteristics? So there are few characteristics which we should see before solving any problem, that whether this problem has these characteristics or not, and if those characteristics are there, then that problem can be solved using dynamic programming. So first the characteristics of a dynamic programming problem is overlapping subproblem. So overlapping subproblem means that the problem has subproblems in it. That means, does this problem involve solving subproblems again and again? So for example, if we take a Fibonacci example, that's a very basic, easy example on lead code. I'm just taking that. So in Fibonacci number, what happens is, this is let me just go through the Fibonacci. Okay, I have already opened it. Let me close it. So this is the Fibonacci example, right? So in Fibonacci, what happens is, if we want to calculate F7, that is Fibonacci of 7. So basically, first, what is a Fibonacci number? Fibonacci number is Fibonacci n is equal to Fn minus 1 plus Fn minus 2. So previous two numbers added to create a Fibonacci number. Fibonacci number 0 is always 0, 1 is always 1. For 2, we'll have Fibonacci 1 plus Fibonacci 0, so it will become 1. For 3, we'll have 2 plus 1. For 4, we'll have 3 plus 2, and so on. So for example, if we see here, if you want to calculate F4, then we have to again calculate F2, right? And for calculating F3, we have to again calculate F2. So F2, there are two calculations of F2 here. So if we do not store this F2 somewhere in cache, then we have to again calculate this F2 while we are trying to calculate F4, right? So that's how the repetitive subproblem or overlapping subproblem characteristic is there. For example, in F5, if we see, for calculating the F5, we have to calculate F4, F3. For calculating the F4, we have to calculate F3 and F2. And for calculating F3, we have to calculate F2 and F1. So now, if we do not cache this F2, Fib2, so we have to again calculate this F2, and this whole block, that is this F1, F0, will be repetitive again. And again, for this F2, this two blocks, these two calculations will again be repeated. So that's the Fibonacci number satisfies the overlapping subproblem property. That is, this problem involves solving subproblems again and again. Then there is another property called the optimal substructure property. So if optimal means a feasible solution. If a optimal or a feasible solution can be constructed from optimal solutions of subproblem. For example, if we see here, for F4, the solution of F4 depends on F3 and F2. The solution of F3 depends on F2 and F1, right? So the optimal solution, that is the intermediate solution, depends on two previous solutions, right? That is solution of its subproblems, smaller problems. So this again satisfies the optimal substructure property. Then again, The problem statement in dynamic programming often has something as minimum, maximum, longest, largest, or the nth number. So here in our case, it's a nth Fibonacci number. And this property, we can also see that the greedy approach should not fit in some particular use case. So this can also be seen in some of the dynamic programming problems. So now there are two approaches to it for the dynamic programming. One is a top-down and other is the bottom-up. In top-down, as its name says, we start from top and then we goes to bottom. That is, we take a case, we consider the nth case. That is how we derive the nth number, and then we dive to the base case. That is the 0 and 1. For example, here we have the base case. This is for the ith or the nth number, and this is how the logic goes. And in the bottom-up approach, it's opposite. We go from um, base case to up. That is bottom up. So we'll just see this top-down approach. This is easier. It involves recursion, and it's also um, but it's easier and but it's less faster because stack allocations are not there in bottom up. So even stack allocations lead to higher space complexity. So now let's look at the dynamic programming template. So basically, there are 5 steps to any dynamic programming problem. So first of all, we have to define the state. So state means, so for example, there is a question called the climbing stairs. In climbing stairs, um, let me climbing stairs lead code. Let me open this as well. So we are just taking this question as a reference to understand the dynamic programming template, but we'll solve the Fibonacci number using the dynamic programming. So what happens here is the question says that you are climbing a staircase. It takes n steps to reach the top. Each time you can climb 1 or 2 steps. How many distinct ways you can climb to the top? Right. So we have a staircase, and let me just open this as well. I think I have just, oh, this, okay. I think it's, so we have a staircase in which we can climb 1 or 2 steps at a time. So it says how many ways we can reach to the top, in how many ways we can reach to the top of the floor, right? So how the DP templates, how the DP template is applied and what is the state here. So state in the climbing stairs means reaching nth stair, and in case of Fibonacci number is finding the nth number or reaching the nth number, right? So state is number of ways to jump onto the nth stair. So whatever we want as an end result, we can consider it as a state. So let me just write it down here. So in case of in or I'll say Fibonacci number, one state is equal to um, finding the nth number. Okay, then we have a function to return a state. So in every DP problem, we can have a function or a block. So this function can be inside the main as well. That is, this block basically can be inside the main, or we can keep a separate function itself. So this function actually returns the state. So this means that this function will return the nth Fibonacci number here. So we'll have a function to return state. So in our case, we'll have dp and it'll take I and it'll return nth Fibonacci number, right? So third step is the recurrence relation. So this is very important. So in any dynamic programming, there uh, is a property called the overlapping subproblem and optimal substructure. So it means we can derive the result of nth state or nth number from previous numbers or previous state, right? And that's what the recurrence relation. So recurrence relation means the relation to transition between states. So here in this case, if we see uh, a reoccurrence relation, sorry for the bad spellings, recurrence relation. So the nth fib number would be equal to n minus 1 fib number plus n minus 2 fib number, right? So any number can be derived out of it. Then 4 is the base case. So in dynamic programming, the base case we have to derive from the logical thinking. So just um, remember, we have to apply our logical thinking. We have to look at the question, then think logically. So base case for the Fibonacci number, that is Fibonacci number 0 is 0 and Fibonacci number 1 is 1. So it's already given in the question. But in some of the questions, it's not given. We have to derive it. Then after the base case, we have the fifth property that is called caching or memoization. This is important. So in memoization, we store the result of intermediate calculations. So in our case, we'll have a vector or array, um, something as memo we can say, and we'll store um, the it will be of size n or something, and we'll store every Fibonacci number in this array. And before returning the result, before returning any or calculating any Fibonacci number, we'll just check that the number is present in it or not. If it is present, then we'll return from it. Otherwise, we'll calculate it. So these are only 5 steps, and in every dynamic programming problem, you can just apply them. So let's go to the Fibonacci number question and see how we can solve this question using this. So first of all, we can assume that if n is equal to 0 or n is equal to 1, so in that case we can return n. So this is a base case which can be applied in that function which returns the state, but I have applied it already. Now, if we want to calculate nth Fibonacci number, so let me take a vector. Um, I'll say vector fib number, and its size will be equal to n, and I'll initialize it to 0. Um, so it's something I have taken a vector, and then what I'll do is I'll store 1 in 1, right? So the first vector, first entry would be 0, second would be 1, and all apart are zeros, something like this, right? Now we want to calculate the nth Fibonacci number. So how we'll go about it? I'll do a dp. This is the function to calculate uh, the Fibonacci number, and I'll do n, right? So int dp, I'll take the vector and vector of fib number comma int n, right? So we remember that we have a recurrence relationship. So dp of or rather I'll say vector of fib number n is equal to n minus 1 plus n minus 2, right? And again, if so, let me initialize it with minus 1 rather, because 0 is a valid Fibonacci number, right? So 0 and 0, okay, and this will become now minus 1 minus 1 minus 1 minus 1 and so on, right? So now I'll just see if this is equal to minus 1. It means that I have to calculate the Fibonacci number. So in that case, apply the recurrence relationship and just return the Fibonacci number n. And if it is not equal to minus 1, then in that case just return this number only, right? So I think this should be enough. And we can have, or either we can just directly return from here, right? Let me just run the code with any sample input. Okay, so I got an error here. Uh-huh. Okay, so this is from the nth Fibonacci number, so I'll take n plus 1 because 0 nth if it says fourth Fibonacci number, so it will be 0 1 2 3 4 fourth Fibonacci number, but I was taking an array of 1, so let me just try running it now. Okay, now it's good. So now instead of 4, let me calculate it 8. Oh, wrong answer. Output is minus 2, expected is 21. Let me see where it's going wrong. So I have taken Fibonacci number as 0 and 1, Fibonacci number dp. So I have taken dp and int n. Okay, if vector of n is okay, so this is wrong here. I have to uh, call it with n minus 1, and then I have to call it with n minus 2, right? So I'm just calling repeatedly this because this is a top-down approach. I'm calling this function in recursion to calculate the Fibonacci number. Let me calculate it. Okay, now it's fine. Let me submit it. So it's faster than 100%. That's good. So now let me just go back once again and see how we applied our dynamic programming template here. Okay. So our dynamic programming template says the state is finding nth number, then function. So this is the function for finding the state. Let me comment here. Function to find state. Then I have, it returns the nth number. This is nth number. Then it has the, so we have to define the recurrence relationship inside the function. So this is our recurrence relationship. And then we have to define our base cases. This is our base cases. And then we have to do a caching or memoization. So caching, and for caching and memoization, we have done this here, right? And this way we can solve any dynamic programming problem.